So today we start Module 5, the topic, Fourier analysis and partial differential equations. Yeah. So the partial part, I want to give you some relatively simple introduction and some simple examples, just give you some basic ideas. Yeah. So that's the partial differential equation part. Yeah. The Fourier analysis, that's our main topic in this module. Yeah. All right. Today, part A, introduction to Fourier analysis. Yeah. So at the beginning, I want to, give you the background information. So why we need to use the Fourier analysis. Yeah. Here we need to connect to our experience. Specifically, I want to relate it to the power series solutions. Yeah, so something related. So this Fourier analysis, Fourier series has something related, some properties related to the power series representations. Yeah. All right. Yeah. So my remote control. Yeah. Let me plug in my remote control. Yeah. All right. Yeah. When we start, we need to study a special type of functions we call the period functions or periodic function. Yeah. Period. Yeah. Periodic. Yeah. Sine cosine. Sine cosine function. They are well-known periodic functions. Yeah. But we want to study a large class of periodic functions. Yeah. So in our engineering applications, why we want to represent, why we want to use periodic functions. Yeah. There is some good reason. Yeah. Model periodic phenomenon. Yeah. Yeah. So in our real world life, we have a lot of phenomena. Yeah. Related to periodic things. Yeah. Here, I just give you an example. Rotating parts of machines. Period, right? Periodic. Yeah. Rotating parts of machine. Yeah. Another, alternating electric currents. Yeah. That's another important periodic phenomena. Yeah. And or the motion of planets. Yeah. That kind of periodic. Okay? Yeah. So a lot of periodic phenomena. Yeah. Yeah. So here you can see, yeah, we need to have some good representation. Yeah. Because here we treat that periodic phenomenon property. Yeah. That property. Yeah. So that's the important structure in our functions. Yeah. So when we represent these functions, yeah, here we use when we do representation. Yeah. So last time I mentioned the approximation idea. Yeah. So in our real world applications, most of the time we need to do approximation. Yeah. Because it's very hard to represent everything exactly, right? Yeah. So approximation is most commonly used way to represent real world phenomenon, objects. Yeah. All right. Here we do the approximation. Yeah. All right. So here we need to do the approximation. Yeah. But the question is how to do the approximation. Yeah. When we do approximation, we want to do good approximation. Yeah. All right. Yeah. If your structure, if you choose the appropriate structure in your function representations, then you can have good approximation. If you choose a wrong structure, okay, the structure not compatible, when you structure two different objects with structure not compatible, then your approximation will be very bad. Yeah. So that's the point. Yeah. So when you choose the model functions, here we can call model functions, modeling. And when you do the modeling, yeah, you need to, the first thing, you need to make the structure right before you do the modeling. Yeah. All right, yeah, so here, how to represent so many different types of periodic functions. We want to choose the simple and powerful way. Yeah. First, we like relatively simple representation. Second, we want our representation, support a lot of operations. Yeah. The powerful. Yeah. So here, good example, yeah, sine, cosine. Sine, cosine. Simple. Yeah. Nice functions. Yeah. Sine, cosine. Powerful, also powerful, right? When we can take derivatives of any order on sine, cosine functions. Yeah. And they are periodic functions. Yeah. So if you use sine, cosine to represent the general periodic functions, then if you look at the structure-wise compatible, right? Yeah, compatible. Yeah, we use nice periodic functions to represent the general periodic functions. Yeah, that makes sense. Yeah. All right. Now, definition. First, although we are familiar with the periodic functions, yeah, but we want to define it first. Yeah. Very simple definition. A function f of x is called a periodic function if f of x is defined for all real x. Yeah. The domain of the function is the whole real axis, except possibly at some points. Yeah. So if there are some special points, scattered, isolated, scattered. Yeah. So here the meaning. Yeah. So because people may ask, what do you mean at some points? Yeah. So typically we understand in this way. First, these points should be isolated points. Okay. Yeah. Scattered, isolated points. Yeah. And because it's a periodic function, in each period there are finitely many scattered, isolated points in this function. Yeah. Usually we understand in that way. Okay, yeah. And if there is some positive number p, yeah, period, yes, this little p, we want to use it to represent the period concept, called the period of f of x, such that f of x plus p equals f of p for all p. Yeah. You just move to another period. Yeah. Sorry. I need to. All right. Yeah. We need to. So here you can see when you shift, when you make, yeah, because x plus p. So this p is a fixed now, always fixed. Yeah. For any x, so you look at the value, you do the shift, you add x by p units. Yeah. At that point, they have the same value. Yeah. If that property, So we, yeah, good. All right. So that's the periodic function definition. Yeah. But here, well, if you define, yeah, so this is the original definition of the periodic function. Yeah. If you define in this way, then one thing you need to be careful, yeah, because there is this simple property we need to consider. If f of x plus p equals f of x, then f of x plus n times p, yeah, n integer, yeah, n times p also equals f of x. Yeah. Any integer multiple of that p, also period. Yeah. Then you have so many periods. So when you talk about a period of function, which one do you mean, right? So in order to make our discussion easier, yeah, so we make a concept, fundamental period. Yeah. The minimum, yeah. When we say the period, we want our period is the smallest positive period. Yeah. The period we choose, yeah, smallest p, yeah, and that p should be a positive number, period. Yeah. Not negative number, yeah, positive p, oh sorry, such that we have this equality. Smallest positive p to make this equality hold. Yeah. Then we say it's a fundamental period. Yeah. Yeah. All right. Yeah. In that way, no. So when we talk, yeah, actually in our discussion, when we talk about period, by default we refer to this fundamental period. Yeah. Sine, cosine, the fundamental period, 2 pi, yeah, fundamental. Yeah. Tangent function, cotangent function, fundamental period of pi. Yeah. Yeah. Things like that. Yeah. But most of the time, people do not say fundamental period. Yeah. Right? Yeah. People just say period. Okay. Yeah. So here I want to say like this: our default period. Right? When we say period, our default period, fundamental period. Yeah. Yeah. So that's, usually all the other people, they do in this way. Yeah. All right. Trigonometric series. This time we consider trigonometric series. To understand trigonometric series, we can relate it to our power series representation. We just learned power series representation. Now, completely different trigonometric series, yeah, representation. All right. Yeah. Here, the typical trigonometric series. So what do you mean, the trigonometric series? Yeah. Here you can see, yeah, it's a summation. In this summation, we need to include all these terms. Yeah. First, a constant term. Yeah. We need a constant term. Yeah. So the constant term, actually, you can, yeah, relate it to, because look at it. Cosine x. Cosine 0 equals 1. Yeah. The constant term, actually, it means this constant a0 times 1 times cosine 0. Yeah. Yeah. Still, yeah, because you can put this term in the category with cosine terms. Cosine terms. This constant term should be, characterized in the cosine terms. Then the sine terms. Yeah. 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 So and sine function, cosine function, and you keep all the form cosine nx and sine nx. All those terms. Yeah. Yeah. So you may ask, why we include all these terms, right? Yeah. So this question, to answer this question, yeah, so we need to go to one level higher, yeah, higher level, okay, in math to understand this question. Yeah. Yeah. All right. Yeah. So I will answer this question later. Yeah. All right. Trigonometric system. Yeah. This concept, the system. Yeah. So here, when we talk about system, here we need to relate it to a concept, the basis concept. Yeah. In this class, we use this basis concept a lot. Yeah. The basis of our solutions of ODEs, right? Yeah, the basis functions of our second order ODE solutions. Yeah, we use basis concept. So a lot of places we use this basis concept. Here, we need to use this basis concept again. Look at the system. Yeah. So here, all these functions we use to define a trigonometric series. Yeah, these functions. Yeah, we put them together. Yeah, yeah. So we form a trigonometric system. Okay. Yeah. And the functions in this system form a basis. Basis. Basis for what? Basis for something, right? Yeah. Basis for a class of functions. A class of functions. Yeah. So, yeah, basis for a class of functions. What class of functions? Right? So when you say class of functions, because this expression very vague. What class of functions? Yeah. So this class function, very special. Square integrable function. Have you heard of that? Square integrable function. That class, square integrable. Okay? All right. So this class is a very important class in our real world applications. It's called a square integrable function. I will explain this class. Square integrable functions. Yeah. So that is, what's the square integrable? When you take integral, okay? Integral, yeah, in some interval, yeah, here let me write AB, okay? Yeah. Yeah. This AB, we can even extend to infinity, okay? If we need, yeah, infinity, yeah. F function, yeah, square, yeah, yeah, because square, you don't need absolute value, square. But for complex value, you need to take square. Here, if we just use the real function value, yeah, we don't square. And we take square, less than infinity. Yeah? Less than infinity. Yeah. This we call a square integrable. Yeah. That means when you take square, then integral, then it is defined. You can find it. Yeah. Less than infinity means convergent. If you take the integral, it's convergent. The integral is convergent. If it's infinity, divergent. It's integral divergent. Yeah. All right. All the classes together. Yeah. All the classes together. We can use these trigonometric functions to represent square integrable functions. It's a basis. It's a basis. Okay? Yeah. Basis, that means if we use these functions to represent square integrable functions, then we won't miss anything. Okay? We won't miss anything. Yeah. Yeah. There is no hole. We cover everywhere, right? We cover everywhere. Yeah. Because here, later, when we see some theorem, so you will see, theorem. After we see the formula, you will know, oh, we do not miss anything. Yeah. Yeah. Yeah.
Is that true for only this period, like the period of these functions?
Yeah. So here we consider, right, one period. Okay, one period, because this one, this function, yeah. So in this place we consider 0 to pi. Okay, yeah. So if you use this as the basis, we need to represent integral on one period, 0 to pi. Yeah. But later you will see, we can multiply some constant. Okay, so we, when we do some adjustment, then we can cover any interval, any AB interval. Because AB interval, we start from the standard interval. We can scale it, right? We can shift scale. Then, if we have our results, we can do some simple operation to get that. So then we don't, in the real world application, we don't worry about what interval. Yeah. So we only develop our theorem on the standard theorem. Then real world, because real world we will do on the general interval. Yeah. Then we just, do some operation to get there. Yeah. So we don't worry. So when I write AB interval, any interval. Yeah. So if it's square interval on any interval, then we can use, some related basis functions, scaled related functions to represent. Yeah. Yeah. All right. Yeah. Convergence of trigonometric series. Yeah. Because you have infinite, this is infinite series. Yeah. So we need to consider the convergence issue. Yeah. So it's very complicated. So in this class, we just look at the results. Yeah. Yeah. All right. The trigonometric system is orthogonal. There is another concept called orthogonal concept. So what's orthogonal? Orthogonal, okay? Yeah. Perpendicular, yeah. Geometrically, yeah. So in math, this concept, if you look at from the geometry, perpendicular, orthogonal, right? Yeah. So the definition is like this. You take integral, yeah. So here, because you take integral of the product of two functions in the system. You say select arbitrary two functions in the system. Yeah. So one you use m multiple, another use n multiple. But these two numbers are different. When these two numbers are different, yeah, all right. So you have these. Yeah. The integral, the product of these two functions, then you take integral, it's 0. Yeah. But for this case, because sine function, cosine function, there are two different type of functions. In this case, even m equals n, it is still true. Yeah, m equals, yeah. Because the different type, yeah, the difference is already very big. Yeah. So even m and n are the same, you can still use, yeah. So if you do some simple calculation, you can see it's 0. 0 means orthogonal. Yeah. These two functions are orthogonal. Okay, orthogonal. All right. Then two functions of the same type, both cosine. Then this time, you need to use these two integers must be different. Because if two integers the same, cosine square is a, positive, right? Then you take integral, the area of cosine square must be positive. It cannot be 0. But if these two numbers are different, always integral of the product, always 0. Similarly for sine, nx, mx, different m and n, the integral also 0. So this property we call the orthogonality property. So, and these basis functions, if they have this orthogonality property, we call it orthogonal basis. Orthogonal basis. Orthogonal basis is very convenient. Later you will see. Orthogonal basis is the best basis. Best basis. So if you can find an orthogonal basis, your formula will be very simple. So when you write your, function expression using these basis functions, the best you can get. Later you will see. Why the orthogonal basis functions? That's the most desirable basis functions. All right. So this concept. These functions are linearly independent. So here that means if you have a set of functions, so here, I want to say in this way. So here I talk about this property, general property. A set of orthogonal functions, or orthogonal. So imagine, set up implies all the functions in the set, they are linearly independent. This property. Because the orthogonal property is much stronger than linearly independent property. So the stronger one implies the weaker one. Linearly independent is weaker than the orthogonal property. So this is stronger. Because orthogonal, every two, if you take, 0, If you want to prove, very easy. All right. So here, let me write a simple proof. Orthogonal. Suppose we have a set of functions f1, f2, fn. Orthogonal. Orthogonal means here here, let me, for simplicity, I just use one period. Fi times fj dx equals 0 for I not equal to j, right? That's the orthogonality definition. All right. Now, let me show you. They must be independent. All right. Independent, what's the meaning of? So let's write a general linear combination if we can find these k. K1 F1 times K2 F2 Kn Fn equals 0. Linearly independent means this implies all the k's must be 0, right? That's the linearly independent. If you can find certain case coefficients for these functions, adding together equals 0, then by the orthogonality, you can imply these coefficients must be 0. How? Let's take integral both sides. How about that? Okay? So here, let us take integral. Let us multiply f1 both sides. How about that? Still 0, right? I use f1 multiply the sum. Yeah. 0. All right. Then, can I take integral from both sides? Because 0. All right? Yeah, 0. Take integral 0. All right. Then, look at if we write it separately, yeah, k1 0 to pi f1 squared dx. This integral is a positive number, right? Yeah. So here, our x, we assume, it's a non-zero integrable function, square integrable. What's non-zero square integrable function? Okay. Yeah. All right. Other than the first term, all the remaining terms 0 by orthogonality. All the other terms 0, right? Yeah. Equals 0. Can you get k1 equals to 0? K1 must be 0, right? Yeah, because that integral is non-zero. Yeah. So k1 must be 0. All right. In this way, can you prove k2 must be 0? Yeah. You multiply f2. The second time you multiply f2 both sides. So you get k2 must be 0. All the way to the last one, fn, kn must be 0. All the k's must be 0. These functions must be linearly independent. Yeah. So the orthogonality implies linear independence. Orthogonality is much stronger than linear independence. Yeah. Yeah. All right. So that's this property. Yeah. So that's why I say orthogonality is a very desirable property. Yeah. We want to have. All right. Yeah. So yeah, here. Yeah. Yeah. Because yeah. All right. So here you can see. Yeah. Represent a period in. Yeah. So the next question. Actually, this question is a very important, big question in math history. In math history, Fourier answered this question. Yeah. Fourier wrote a paper. Yeah. Find a representation. Yeah. All right. Euler formula for Fourier coefficients. Yeah. All right. Suppose that f of x is a given function of period 2 pi and is such that it can be represented by all right. Yeah. All right. Then, how to calculate these coefficients, right? Yeah. Because if we want to represent a periodic function in the trigonometric series, how to calculate the coefficients? Yeah. By orthogonality. Here you can see we use the orthogonality, similar to what we did, both sides. Can we multiply both sides by one of the functions? Right? Yeah. You multiply, yeah. So now you just do integral both sides. On one period, so one period here we select symmetric period from negative pi to pi. This interval is a symmetric interval. Yeah. Right? Yeah. With respect to 0 point. Pi, positive pi, negative pi. Yeah. Then this interval symmetric. Okay. Positive part, negative part, symmetric. Yeah. So that's the reason. Yeah. Most people, they like to choose a symmetric period to represent their functions. Yeah. All right. So now you can see you will take integral both sides. Yeah. The integral of all these terms, all 0, right? Yeah. Remember orthogonality? Yeah. All these inside, look at this. Integral from negative pi 1 times cosine of nx. Yeah. If these, because when these functions are different, the integral is 0, yeah, by our orthogonality property. Yeah. For sine, different, 1 cosine x. There are two different functions. So the product integral 0. Yeah. All right. So you can see the integral of all the other terms 0, then the integral of this pi to pi, that's 2 pi times a0. 2 pi times 0, you divide it by 2 pi. So you have this formula. Okay? a0 equals 1 over 2 pi. Then the integral of this function. Yeah? Right. All right. For the other coefficients, you can do the same thing. By the orthogonality. Only one term, the integral is not 0. All the other terms, the integral all 0. So that one term, yeah, so you can use, yeah, to find this coefficient. Yeah, that's simple. Yeah. All right. Yeah. Here you can see this formula is very important. So yeah, Fourier discovered this formula. Yeah. That's a big contribution in math. Very important discovery. Yeah. But at that time, this result was not accepted by the math community. Yeah. So they, those mathematicians, because Fourier submitted his paper to some well-known, famous journal, the math journal, but got rejected. This result. Yeah. So any periodic function can be represented in this, trigonometric sequence. Yeah. Yeah. So those experts, so they felt your representation. How do you know it's convergent? Because there is a convergence issue, right? Yeah. Yeah. It may not be convergent. So although you can calculate coefficient in this way, but how do you know if you represent f function in this trigonometric series, how do you know both sides are the same? Yeah. Yeah. So, yeah. Yeah. So that result was rejected. Yeah. But after many years, yeah, and definitely after a lot of improvement, because a lot of mathematicians, they need to study the convergence. Yeah. The convergence is an important issue. Yeah. After they prove the convergence result, then this result can be accepted. Yeah. There is a convergence problem. Yeah. Later we will see. Yeah. That convergence result. Yeah. Yeah. But that's a breakthrough. Yeah. So this view, this representation is a breakthrough. Yeah. All right. Yeah. Yeah. So here we assume convergent. Yeah. But later, there is a theorem, telling us the convergence. What's the convergence property given from the trigonometric series? Convergence property. Yeah. Yeah. We will see that. So, yeah. All right. Periodic rectangular wave. In our engineering applications, we use periodic rectangular wave phenomenon a lot. Modeling. Yeah. And yeah. So let me look at the time. Yeah. All right. So here we do a practice. Yeah. Practice. Yeah, because we will do rectangular wave a lot. Yeah. All right. Find the Fourier coefficients of the periodic function f of x. Apply the formula from the previous screen. That's simple. Yeah. All right. Here we define periodic rectangular wave. How do we define it? So this is the function. In one period between negative pi and pi, so one symmetric period. So it's a, negative part, positive part. Yeah, rectangular wave. Yeah. All right. Then we do the periodic extension. So this formula gives us, we do periodic extension to cover the whole real axis. Yeah. Yeah. All right. So the graph like this. Yeah. So that's the rectangular wave. Yeah. All right. Then we just plug in the formula. We calculate the formula, right? So an, we plug in. Yeah. So because you have the negative half of the interval, yeah, positive half of the interval, yeah. So then you do calculation, yeah, get a 0. Yeah. Because negative side, positive side cancellation, right? Yeah. Negative area, positive area, the same, cancel out. Yeah. So all the an coefficients all gone. Okay. Yeah. So you only have the b. Yeah. So all the a coefficients all gone. Yeah. Yeah. A0 also 0. Yeah. And the b coefficients, you cannot cancel out b coefficients. Yeah. All right. So negative, yeah, because sine also negative, right? In the negative half, sine also negative. Yeah, not necessarily negative. Yeah, but yeah, nx. Yeah, but it cannot be canceled out. Yeah, yeah, sine, and, yeah, could be complicated. So lot of periods inside that function. Yeah, up, down. Yeah, but cannot be canceled out. Yeah, when you do the calculation, yeah, you get a non-zero represent. Here you can see for some n you can cancel out, right? For even n, here for even n you can, because 1 minus 1, even n 1 minus 1. For odd n, 1 minus negative 1, 1 plus 1, 2. Yeah. Yeah. So what do you get? For odd subscripts, yeah, you get a non-zero. For even subscripts, you get a 0. Okay? Yeah. So, but you can write a representation. This is the trigonometric series representation of this periodic rectangular wave. Yeah, interesting. Yeah, yeah, yeah. Going back to early history, yeah, people feel, how can you represent the function like this? Yeah. Using cosine function. We know cosine function very smooth, right? The curve, yeah, so smooth. But this function is not smooth. This function, a lot of breaking points, right? So many discontinuities. How can you use nice, smooth functions to represent discontinuous function like that? Yeah. At that time, there were no computers. No computers, right? Yeah. Yeah. At this time, if you want to see how they can be the same, how these functions, these two representations could be the same, people could use computers to do calculation, right? Yeah. So you can use computers to calculate, term by term, adding together, so easy. At that time, so no computers. Okay? Yeah. How to see? Yeah. They are the same. Yeah. We can see here. Yeah. Does it make sense to use a sequence of continuous functions to approximate a discontinuous functions? Yes. Yes. Yeah. All right. So let's look at. Because here, although a sequence, but we take infinite summation, right? Infinite summation, then the behavior How do you predict the behavior of infinite summation, right? The behavior could be, unpredictable. Could be anything, right? Yeah. All right. Yeah. So here, let me do the approximation, because here we need to use the approximation idea to see it. Yeah. All right. How to do approximation? Yeah. Let's do approximation term by term. How about that? The first time, we just take the first term. We draw the graph. That's easy, right? The second time, we add one more term. We use 2 terms. How about that? So we get a better approximation. Then the third time, we add another term, 3 terms. Then better, so the approximation becomes better and better, and eventually the same. Eventually the same, right? Let me show you the graph. All right. So here we define the partial. This is the partial sum concept. Yeah. Remember, in our power series, we do the partial sum. Yeah. Here in our trigonometric series, we also do partial sum definition. Then it is well defined, partial sum, because you never need to worry about the convergence, right? Partial sum. So it's a well-defined function. No convergence question to be asked. All right? Yeah. All right. Now let's draw the graphs of these partial sums. Yeah. S1, yeah. Partial sum only has 1 term. Yeah. S2 and S3, and so on. Yeah. You can draw, because, well, if we use computers, we can draw any number of partial sum, right? 100. It's very easy. We write a program, 100. But at several hundred years ago, yeah, probably 400 or 500 years ago, how do you add up 100? How do you do the sum, partial sum of 100 terms? Nobody can do that, right? Yeah, nobody can do that. 100 terms. Here, yeah, we can do it easily. Yeah. All right. So 1 term, the graph like that. Okay. Second term, better approximation, right? Third term, even better, right? So you can imagine when you add more and more terms, then approximation becomes better and better. Yeah. Very close. Very, very close. Yeah. Yeah. But never be the same, never be the same, but very close. Yeah. The error could be controlled, as small as possible. Yeah. If you want to specify certain error, you can always make the sum. You can always choose the number of terms such that the error is within that specified number. Yeah. 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 So in that way, you can see, yeah, great approximation. Yeah. All right. Yeah. 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 Understand now. Next, the discontinuity. Yeah. Next, yeah. Let me go back to the that why the paper, Fourier's paper, was rejected. That question, yeah, because the convergence question. Convergence question, yeah. So if you do study the convergence property at the normal points, what's the normal points? These points, these are the normal points. Normal points, at these points, the function is continuous. Continuous, that's the normal points. If at no points, yeah, then convergence has no problem. Convergence has no problem. The same. Both sides the same. Okay? Left-hand side, the function value at the continuous points. Trigonometric series, you plug in, yeah, the point, yeah, both sides match exactly. Yeah, that can be proved mathematically. All right, that can be proved mathematically. Yeah, not too much hard. Yeah, but the convergence may have some problem at the discontinuity. Because this, yeah, so let's say the point at 0 point discontinuous, right? The function is discontinuous. Yeah. At a pi, discontinuous. At 2 pi, discontinuous. Yeah. So when you calculate the values at both sides, well, because left-hand side, at 0, at pi, the value is even not defined, right? Yeah. If you look at this rectangular wave, at 0 point, the value is not defined. What's the f of 0? You don't know, right? Here, no definition in this function. Yeah. But if you look at if you do the summation of that trigonometric series, you plug in 0, which number do you get? You plug in pi, which number do you get? You plug in multiple of pi, what number do you get? Right? Yeah. So after the break, let's take a 10-something minute break. After the break, when you come back, let us look at the convergence question and the discontinuities.